Hello everyone and welcome to the 5th 3D Buzz Math VTM. My name is Rob Rulnick, known on 3D Buzz simply as Demondo, and with me tonight we've got
Logan Frank.
So, in this 5th VTM, what we're going to be talking about is triangles and properties of triangles. Now, some of you may be wondering, well, a triangle is really simple, I know what it looks like, what's there to talk about? This surely is going to be a very short lesson. Well, not quite. There's tons of properties of triangles, and they're extremely important to know about for geometrical constructions, and because any polygon, or any regular polygon, which I'll talk about in a later lesson, can be broken down into triangles. So keep that in mind when you realize this is a base, it's a foundation for future polygon constructions. Okay, so let's begin. We'll start with some solutions to the previous problems. From lesson 4. Now, as you can see, I converted to all the different forms. You might have chosen other ones when you're converting between forms of writing a line. So I use the intercept form, the general form, the point-slope form, and the slope-intercept form. You might have chosen other ones, but all of our answers should be equivalent.
If you happen to choose these, this is what the answer would be.
Let's hope. And and then here, these are the answers for their points of intersection. So the first answer was they're coincident lines. They're parallel and overlapping, so they have every point in common. And then here are the points of intersections for number 2 and 3. So let's move on. Triangles. Triangles are polygons with 3 sides and 3 angles. The sum of all the angles in a triangle is 180 degrees. We'll be showing you that why that's true a little later on. And the sum of the lengths of any 2 sides of a triangle is greater than the length of the third side. Now, you might be wondering, why are there all these names? Equilateral, isosceles, scalene, and so on. Well, it turns out you can define a triangle based on its sides, or its angles, or both. If you're defining the triangle based solely on its sides, then equilateral is a triangle with 3 sides in common of equal length. Isosceles triangles have 2 sides of equal length, and scalene triangles have all 3 sides being different lengths. It's important to note that an equilateral triangle will have 3 60-degree angles, and in an isosceles triangle, this side, which is opposite to one side of equal length, this angle rather, would be equal to this angle, which is opposite to the other side of equal length. So if this was, let's say, I don't know, give me an angle, 60 degrees, then this would also be 60 degrees. Both of them would be equal.
So it really wouldn't, because it's not equilateral, but
right.
Let's say they were 30 degrees, the other one would be 30 degrees.
Exactly. And then this would be like 100 degrees, or 120 degrees, or something like that. So these 2 x's
all
would
the
be
same,
equal.
whatever they are.
All the same, in an isosceles triangle, those 2 would be equal angles. An acute triangle has all 3 angles being acute angles, meaning less than 90 degrees. A right triangle has 1 angle of 90 degrees and then 2 other angles. And an obtuse triangle has 1 angle of greater than 90 degrees. So, for instance, you could have something known as, let's say, a right isosceles triangle, or an isosceles right triangle, in which case there'd be a right angle, and these 2 angles would be, these 2 sides would be equal. As a result, these 2 angles would be equal. And since all 3 angles in a triangle total 180, 180 minus 90 is 90, divided by 2 is 45, so each of these would be 45.
45 degrees.
If it was an isosceles right triangle. So moving on. Triangles part 2. The perimeter of a triangle is the sum of the lengths of its sides. So, in this example, one side is called A, the other B, and the third C. So, A plus B plus C is the perimeter.
Simple enough.
Very simple. The area of a triangle can be attained in several ways, including 1/2 base times base times height. And the reason this works is that if you think about it, this triangle is encased in a box, a rectangle. The area of a rectangle, as many of you must know, is base times height. This triangle is actually half of the area of the bigger rectangle. And if you don't see that, then look at this rectangle right here. This part of the triangle on the left is half of that rectangle, and on the right it's half of the other rectangle. Therefore, it totals half of the big rectangle.
I see. If you were to break the rectangle up into two to represent one side of the triangle, then you can clearly see the line that would bisect the rectangle.
Exactly. And then, what happens if you only know the lengths of the sides of the triangle? Then it's still very much possible to determine the area of the triangle using something known as Heron's formula. It looks very, very complicated, but it's actually quite simple. What you do is you start by taking half of the perimeter. So A plus B plus C is the perimeter, and you divide that by 2. For making the formula more concise, I represented that as S. Now, the area is simply the square root of S times S minus A times S minus B times S minus C, which basically means you take half the perimeter and you subtract each side, multiply it all out, and multiply half the perimeter again. Take a giant square root and you get the area of the triangle.
Nice. So it is possible to find the area of a triangle just by knowing its 3 sides.
Right. And it helps to have a calculator for the square root.
Of course. Or if you were using this in a computer program, you could easily plug the formula in. And
exactly. So right triangles. As you might remember, right triangles have a right angle with the little box symbol, meaning it's a right angle. And then there's Pythagoras' theorem, which states the sum of the squares on the legs of a right triangle is equal to the square on the hypotenuse. So what does this mean? Well, the sides, A and B, are known as legs of a triangle. They're the ones that the right angle takes place at the intersection of side A and B. And in any case, these two squares, the yellow square and the red square, if you add them, it's equal to the square in blue, the one that's at C, which is known as the hypotenuse. The long side of a right triangle, that one that I'm circling and it's kind of hard to see, is known as the hypotenuse of a right triangle. So A, the square at A, and the square at B is equal to the square at C. And I'm sure many of you remember this formula from grade school or beginning of high school or middle school or wherever you learned it. But many people do not know the proof. And there are hundreds and hundreds of proofs. But I find the one here to be the most elegant and easy to understand. What I'm saying here is that A plus B squared, so meaning A plus B, meaning this side, squared. So this total area here of the whole thing has to be equal to the area of 4 of these blue triangles plus the area of that big white square. And as you can see, A plus B squared is simply A plus B times A plus B. And then using the distributive rule that we talked about in an earlier VTM, you distribute the A, so you get A times A plus B, and then you distribute the B, so you get B times A plus B. Working all that out, you get A times A gives you A squared by distributing the A, and then plus A times B, and then plus B times A by distributing the B here. Wow, I shouldn't be using red, I think. I'm going to switch to blue.
Just to be clear enough. I mean, it's still just marking around, circling things.
Right. So distributing the B, you get B times A, and then B times B, which is B squared. And if you realize A plus B is the same as B times A, so you have A squared plus B squared plus 2 times A times B, is equal to, now we work on the other side. So 4 divided by 2 is simply 2. So you have 2A times B plus C squared. And then if you go down, we didn't change anything in this line. This line stays the same, as does this line. But then you realize, wait, I have 2A times B and 2A times B. So if you can just cancel them out because they'll have the same value. And if you cancel them out, you have A squared plus B squared is equal to C squared. And therefore we just proved Pythagoras' theorem.
Very nice.
Now, QED is how you end proofs. It's basically, it's Latin. It stands for quod erat demonstrandum, which basically means, I believe it means what was supposed to be shown or what was meant to be shown or something like that. Alternatively, some people end it with just a black box, like at the end of a computer program, or old computer programs. And I just end it with both because I feel like being, double ending. Okay, so now we're going to prove why the interior angles of a triangle sum up to 180. And we're going to be using a method that we talked about in the previous lesson. Now, if you look at this big line up here with the two arrows on top of it, it's actually parallel, and now I switch back to red because I'm crazy. So it's parallel to this side of the triangle down here. So these two are parallel. That's what that little arrow means. So therefore, these sides of the triangle act as if they were... do you remember what that was called, Logan?
As if they were...
Transversals.
Oh, as if they were transversals, that's right.
Right. I had a memory block for a moment. In any case, so these two sides are parallel, and those are transversals, which basically means if you use the alternating angles thing, then here, these two angles are equal. So this angle, in red, equals this angle. Now if I switch to, let's say, green, and I do that again, then this angle here, in green, I hope that shows up in the with the codec, I think it will, is equal to that angle down here. So x and x are equal, and I guess y and y are equal. But then if you take this angle, and we'll call it z, we know one other thing. This line on top is essentially a straight angle, 180 degrees, if you add up x plus y plus z. Angle x plus angle y plus angle z. If you add them all up, they end up being supplementary between all of them. So you get 180 degrees. So therefore, if x is in the triangle, y is in the triangle, and z is definitely in the triangle, then the sum of all the interior angles of a triangle
has to be 180 degrees, just because we've shown that, 180 degrees is a supplementary angle or a straight angle, and we've proven that all angles x, y, and z exist within the triangle, therefore it must sum to 180 degrees.
Exactly. So moving on. Similarity and congruence. Two triangles, A and B, are similar when they have the same angles, and every side on triangle A is proportional to the equivalent side on B. So if you look at these three triangles down here, the red, the green, and the yellow, well, they all have the same angles because they're all equilateral triangles. Therefore, they all have three angles of 60 degrees. Therefore, they're all similar triangles because they meet when they have the same angles. They're all equilateral. They're all equilateral triangles with 60 degrees for each angle. Therefore, they're similar.
So all of them are similar.
Plus, let's say this side was a length 1.
Okay.
And this side was a length 2. Then they all, by multiplying the side of 1 by 2, you'll always get a side of 2. Or rather, I'll make a small change because that might be a little confusing. 2 and where's the eraser tool? Eraser. Boink. Okay. If you're, let's say 2 and 6. Woo. Messed up 6. That's a 6. In any case, if this side triangle, the red one, has sides of 2, and this green one has sides of 6, then any side on the red one multiplied by 3 will give you the equivalent side on the green one of length 6. So there's a ratio between them. The ratio is 1/3. Similarly, two triangles A and B are congruent when they have the same angles and every side on A is equal to the equivalent side on B. So the red and the yellow triangles are equal because of the notation I use. They all have a single bar representing equal size. But in that case, this would be a 2 here. And therefore, they all have 60-degree angles, and all their sides are 2. Now, yes.
So really, with a congruent triangle, that means it's basically the exact same triangle.
As if you went copy-paste and just moved it.
Right.
Whereas a similar triangle is if you went copy-paste and resized it equally in x and y. So you basically scaled it upwards uniformly, or scaled it downwards uniformly.
Right.
So the important thing to remember is that similarity is just a scaling, and congruence is just the same exact thing as if copy-pasted and moved. It might be rotated, but it's the same. So moving on. Similarity. If you know that two triangles have two angles of equal size, then the triangles are similar. And this makes sense. Because if you think about it, if you know two angles in a triangle, angle, angle, and then you know the third angle because they have to be totaling 180.
You can infer the third angle.
So we know this angle here will be equal to this angle here. Therefore, if they've got the same angles, then the only thing that changed, or could have changed, is the length of the sides. And as you can see, this side down here, this side here, is certainly smaller than the equivalent side here, but the ratio between them will be the same for all the other sides.
Right. Well, if you find the ratio between those two marked sides, all the other sides will have the same ratio.
Right. And you might be curious, how do I know which sides are corresponding sides? Because, like, how did I know it wasn't this one down here, for example, the bottom of the yellow triangle? Well, that's really simple. I went from the triple equivalent angle to the single, and therefore this side has to be equal from the triple equivalent angle in the yellow to the single equivalent.
Right, you just grab the line that's between the angles from the first one.
Right, because even if I rotate the triangle, the angle positions don't change.
Of course.
So, there you go. So, that's known as AA, or angle-angle. Now for some congruence. ASA, meaning angle-side-angle. If two angles and the side contained between them is congruent between two triangles, then the triangles are congruent. So as you can see here, you've got two angles of equal size, a single one and a double, and a single and a double, therefore they're equal size, and this side is equal. Knowing that, then you know which direction everything has to go at an angle. So you know this has to go in that general direction, and this has to go in that general direction. And knowing that, they can only intercept at a single point. If you only knew this, and a little direction that's length, and the direction it's going here because you knew an angle. And this length. As you can imagine, if you extended these red arrows, they'd hit here, and that's the only possible point that they'd hit.
Right, otherwise you have to change some of the angles within the triangle.
Exactly. As if you had two lines, and they had different slopes, and they had to hit at a single point. So knowing a side and two angles across from it lets you know that two triangles are equal, they're congruent. So here, we know that the angles are the same, and the side between them is the same for the yellow one.
Right, because just like before, when we looked at the ratio between the lengths of the two sides, if you know that the ratio between those is exactly 1, that means, well, the sides are the same, and therefore the triangles are congruent.
Exactly. And using this, and if you did the same little thing with the arrows, so here and here, you'd see it has to hit at a single point. This length, this side with the single bar crossing through it, this one, is equal between the two triangles. And therefore, if you worked it all out, you'd realize that, hey, they all have the same sides. Their ratio is 1.
In essence, the triangle's basically just been rotated.
Exactly. Congruence part 2. Angle, angle, side. If two angles and the side that's not contained between them of one triangle is equal to that of another triangle, then the triangles are congruent once again. You can use a similar argument to what we used before to show this, so I'm not going to bore you to death. But just remember that angle, angle, side also works, not just angle, side, angle. Moving on. Side, angle, side. If two sides and the angle contained between them of one triangle is congruent to that of another, then the triangles are congruent. So as you can see here, we have two sides that are equal, as you can tell by the bars going through them, and one angle that's equal, as you can tell by that little arc at the angle. And therefore, you know that a third side would have to be equal, because you know where this side ends, and you know where this side ends. And if you connect these 2 points, you have to get the third line, this one. And these 2 points have to be at these locations because you know the angle up here. So same argument for here, and as a direct result, the sides become equal.
And therefore the triangle becomes congruent.
Right, a ratio of 1 to 1. Congruence part 4. Side, side, side. This one's kind of obvious. If two triangles have sides that measure the exact same thing, then the triangles are congruent. So, pretty obvious. If the sides are equal between two triangles, then they have to be equal. Because knowing three sides is only one way of building a triangle with those side measurements.
Because with those three sides, the points are going to occur at the exact places, and they're going to have the exact same angles.
Exactly. So that one's kind of obvious. And then similarity and congruence, part 2. Side-side angle. Knowing that two sides and the angle that isn't contained between them are congruent between two triangles is not helpful. It doesn't tell you anything. Because as you can see here, it's a little mistake. I'll just fix it on the camera. These two have to be, they could be the same measurement, but I'm just saying these two sides, the ones with the double bar now and the single bar might be of different length. That kind of wasn't clear originally. In any case, now that that's clear, fixed on camera, see, no errata needed. As you can see, they have an angle in common and two sides. So angle, side, side, or side, side angle. But clearly, this angle, this acute angle here, is not equal to this obtuse angle here. If you draw a vertical line downwards, you can see that that's an obtuse angle.
And the problem is that line on the bottom, you can adjust the length of that, and nothing is really locking it in place. You're free to adjust it.
Well, you can't adjust it as you wish. Well, you can adjust it within reason.
Well, that's what I meant, within reason, but it's not an exact point now.
Exactly. There's two possibilities where it can occur. Because this length, depending on the angle up here and the angle down here, I'm just making it so the angles are read as different. And this one has 4 because it's not equal to the one up there, the one here. Don't worry about all the notation. Essentially, the concept is if two things have the same notation in angles or sides, then they have to be equal. So I'm deliberately making it more complicated by making them all different. But don't worry if you don't understand that. For now, all you have to realize is that I'll just clear all the ink on the slide quickly, and then we'll just do a summary because that might have been a little confusing to some. Again, I fixed my mistake. So this side with a single bar has to be equal to the other side with a single bar, and the side with the double bar has to be equal to the side with the double bar, and the angle is the same. But as you can see, since this angle up here and this angle down here are free to change because we don't know anything about them, then there's two possibilities, and maybe even more, but I'm going to say 2 just to be safe, where you can build triangles that meet all the requirements but are neither similar nor congruent.
Right.
And if all of this confused you, there's a trick to remember that this doesn't help. If you reverse the letters of SSA, you get A, S, S. And as a direct result, that basically means don't be an idiot, it's not helpful.
I gotcha.
And that's the trick to remember without knowing all this complicated vocabulary. And now we're going to talk about altitudes of a triangle. The altitude of a triangle, or rather the altitudes of a triangle, start at a vertex and are perpendicular to the opposite side. So as you can see, you started at this vertex up here, and you go down vertically, extend the side, and this point would be perpendicular to the side. And like you can see, the altitudes are not necessarily hitting inside the triangle. They may occur outside the triangle. But nevertheless, they just have this requirement. They start at a vertex, and when you draw them, and if needed, you extend the side, they'll be perpendicular to that side.
Okay.
Altitudes are very helpful for when you're calculating the area of a triangle, base times height divided by 2. Essentially, the altitude would be the height. So, all three altitudes intersect at a single point, known as the orthocenter. This point may be outside of the triangle. In this case, the one I just drew in this slide, it's inside the triangle. But I'm going to backtrack for a second. And in this slide, they would extend somewhere off camera in that area, off screen. You'd extend this one like that, extend this one down.
And wherever those meet, that would be the orthocenter.
Yeah. I'm kind of drawing parallel signs, so I'm drawing them differently. Because I meant to draw little arrowheads, but I didn't.
Lines go this way.
Lines go that way. And as a direct result, they'd intercept somewhere off camera down there. That direction. So there you go. And in this one, they intercepted inside the triangle. So, moving on. Properties of altitudes. The lengths of the altitudes in similar triangles are similar and in the same proportion as the sides. Basically, it might not come obviously to everyone, but if you scale a triangle, you're scaling the altitudes the same way.
Proportionately.
Exactly. And then in a right triangle, the altitudes from the right angle to the hypotenuse creates two smaller triangles. These new triangles are similar to each other, and they're similar to the original triangle. So as you can see by my notation, triangle ABC, so from A to B to C, is rather similar to triangle DAC, which in turn is similar to triangle DBA. Now, there's two things to note here. One is the order in which I'm labeling the sides in my triangle. They have to be done in a way that A is similar to D, or rather, I'll change in color and show you. In this one, the one furthest on the left and the one furthest on the right. In the order that the letters are written is meaning that A is similar to D, because they're both first. B is similar to B, which kind of makes sense, because they're both in the middle. And C is similar to A. That's how it's written. So you couldn't write triangle ABC is similar to triangle DBA. Or, rather, BDA. DBA is fine. That's what I did. But you can't write that triangle ABC is similar to triangle BDA. That would be wrong.
Right, because like we were talking about before with with when you have two angles, you find the side in between, you have to, or like if you rotate the triangle, the sides still have to match up, otherwise
right.
You lose the similarity.
Right, so in the notation you're kind of expressing, here's the similarity, this is it. And now if we go back to the vocabulary, here's what I'm saying. Angle A is a right angle. So triangle ABC is similar, let's say, to triangle DAC. Well, D now is a right angle because of properties of altitudes. B, or rather A, we don't really know much about A right now. We can't say that A has to be similar to B. We don't know that yet. But C is an angle in common, so C isn't changing. So A is a right angle, and D is a right angle. C is the same, so it's the same value. And therefore we know that the angle at B and A, or rather, not B and A, but A in this case, down here, in DAC. That from A, the angle CAD. Angle CAD has to be similar to the angle at B, simply because we know that the other two angles are the same value, and knowing two angles in a triangle lets us determine similarity.
That's right.
And you can use the exact same argument for the third triangle. So, moving on. Angle bisector. A triangle's angle bisector goes from a vertex to the opposite side. Pretty clear? Angle bisectors divide each angle into two smaller angles of equal size. So, for instance, if we had an angle that measured 42 degrees, and we got the angle bisector, it would divide the angle into two smaller angles, each of 21 degrees.
Right.
The angle bisectors will meet at a point known as the incircle of a triangle. So I think on the next slide I explain exactly what the incircle is. So let's move on. Properties of angle bisectors. The incircle of a triangle is a unique point. It is equidistant from all sides and is where a circle can be inscribed inside a triangle. So if we look at the drawing, we have a circle, I think it's a pinkish, peachish color circle, inside the blue triangle. But it's touching all the sides, therefore it's it's the incircle of a triangle. It's a triangle. Wow, brain freeze. No, it's the circle inscribed inside the triangle. There.
Right, it's basically the largest circle you could possibly draw inside of a triangle.
And it's in fact the only circle you could draw inside a triangle that touches all the sides.
Right.
The side intersected by an angle bisector is broken into a very specific ratio. And down here I said the ratio. So here's the thing. BD divided by CD, so the length from here, BD, and then the length from D to C, that ratio is equal to the length from A to B divided by the length from A to C. You can't necessarily see that. It's not that hard. Basically, you're saying that, let's say that was a point E. The ratio C to E divided by AE is equal to BC divided by BA. The concept is you go from one side to the point where the angle bisector meets the other side, and then from there to the opposite side and make a ratio. And then you take the side where the angle bisector occurs, that vertex, and go. And
then the two other sides.
Right.
Will have that exact same ratio.
Right. And if you want an easy way to remember it, you're essentially saying BD and CD, and all you replaced was the D you replaced with an A. So now you have AB and AC. So by replacing the D with the A, you get the ratio.
Okay, makes it
or
simpler
the
to
equivalent
remember
ratio.
Just as the formula.
Right. So let's move on. Medians. A triangle's median goes from a vertex to the midpoint of the opposite side. The point of intersection of the medians is known as the centroid. The centroid is the center of mass of the triangle. So as you can see, each of these medians starts at a vertex and then bisects the opposite side into two equal halves. And then the centroid concept basically says if you balance a triangle on a pinhead at the centroid, it would balance fine. Similarly, if you had any piece of rope and you made a line through the centroid, you can balance a triangle on that rope also.
Okay, so you could balance on any of the medians.
Right. Or not necessarily a median, it could be like this line here through the, well, if that went through the centroid properly. That would work too.
Oh, I see. Any line runs through the centroid.
Right, any line. Because the centroid is the center of mass. So a line through it puts the mass equally on both sides.
That makes sense.
Yes, it does. Properties of medians. The lengths of the medians in similar triangles are similar and in the same proportion as the sides. Again, if you scale a triangle, you're scaling the medians uniformly. The centroid occurs 2/3 of the way from the vertex to the opposite side. So let's say we called, I'm going to change in color to red because we have blue on the slide. Let's say this point was A. This point was B, at the centroid was B. I hope that comes out. It's a B at the centroid. And at the opposite side you have a C. The length from A to B is 2/3 of the length from A to C. Equals 2/3 of the length from A to C. And that holds true for any median. So it doesn't need to be at the right angle like I did. It could be on any of the sides.
I see.
Or any of the vertices anyway. So those are equal. Yep. Moving on. Perpendicular bisectors. A perpendicular bisector goes from the midpoint of one side vertically upwards and downwards. So essentially, you find the midpoint of one side, like I did here, and then you just go vertically upwards and downwards.
So basically draw a line at a right angle, perpendicular.
Exactly, a perpendicular line, in both directions. The point of intersection of the perpendicular bisectors is known as the circumcenter. So this point here is the circumcenter. It is the point at the center of a circle that circumscribes the triangle, which basically means it's a circle that hits all the vertices of the triangle.
So just draw a circle through all the vertices, and then the center of that circle will be the circumcenter.
Exactly. And there's only one possible point for the circumcenter. The circumcenter does not always lie inside the triangle. So in this case it did. In another case, it might not. And now for some examples at the end of our lesson. So, calculate all sides and angles in the following triangles. So as you might see, there's two triangles. There's the big one, and there's this small one right here. Right there. There's a small triangle. So the big triangle has a vertical side of length 8.19, a hypotenuse of length 10. And the smaller triangle has a base of 1.91. And using only this information, clear all ink on slide, you have to find all the angles and all the sides of both triangles. And you know this angle is 55 degrees. Examples 2 of 5. Can you solve for x in the following diagram? If you can, why can you? So, is there a value for x? And if there is, how do you know it's right? I'll just backslap. Okay, so just pause the video and solve. Example 3 of 5. Determine the similarity ratio and area ratio for the following triangles. Do you see a relationship? So I'm telling you these two triangles are similar. Knowing that, and knowing that they're similar, in fact, I'll just say that angle, I'll just switch ink color quickly to green, is equal to that angle, and that angle up here is equal to that angle up here. Just so it's very, very clear. These two triangles are similar now. Knowing the information given, can you determine the ratio between the sides and the ratio between their areas? Do you see the relationship? I'll say this up front. I didn't pick the best numbers to see the relationship between them. If you can't, don't worry. If you can, good for you. Examples 4 or 5. So, I've been talking a lot. Logan, you read.
Alright, so, you and a friend are tasked with measuring the height of a nearby building. At a certain time of day, your friend measures the shadow of a 12-inch ruler, standing vertically to be 5 inches. You measure the shadow of the building to be 40 feet. It took you a few tries. How tall is the building?
So, using the information covered in this lesson, there is a way to solve this. Maybe you need to think about it, maybe you need to draw some sketches, but see if you can solve that.
Here's a hint. It might have to do with triangles.
No. I don't believe you. Okay. And finally, examples 5 of 5. Calculate all sides in the following 3 triangles. So once again, there's the big external triangle, and there's 2 internal triangles. Here's one, and clearly above it is the other one. So using only the information given, see if you can solve for the sides of all 3 triangles. And with that, that wraps up this lesson. Thanks a lot, guys.
Very nice. And again, I'd like to thank Rob for walking us through the course material. And as always, I'd like to thank all the viewers who followed along with us. With that, take care, everyone.